Okay. So as I was saying, normally the way we do it is I try to explain as much as possible with the help of the projects that are actually under construction or actually being constructed. So it's very easy to visualize these concepts. But looking at the tight schedule we have this semester, we might have to work on the important or the mandatory things first, and then maybe we could expand the scope as and when possible and look at various projects. So I have categorically segregated the syllabus in three parts. First is a very basic understanding of steel as a material, wherein we'll understand what is called as a steel table. Have you heard of this term before? Steel table.
No.
Yeah.
But is it something like which talks about the different kinds that are like available and
Yes.
all?
Yes. So basically, it is a catalog. Just like you have a catalog for colors, just like you have a catalog for furniture, you have a catalog for what are the standard steel sections that are uh, available in the market, that should be available in the Indian market. Now there's this handbook, or there's this code by the Indian Bureau of Standards, which kind of gives a list of all these standard sections that one can use. But uh, the manufacturers of steel also have their own catalogs, also have their own steel tables, which are more practical to work with, which are easily available in the market. And that is the first thing that we go to whenever we have to choose a section, choose a type of section that we want. So we will just briefly look at what is a steel table and how to read a steel table. Because whenever you are working on a project, whenever you have to decide which type of section to use, the first thing that you should know is whether this type of section is available in the market. And further, in terms of understanding what is given in the table, we look at the properties that are mentioned so that we understand, okay, if I'm talking about, say, ISM V 500 section, what does this mean? And how does it affect the appearance of my structure? How will it look if I provide it in a beam? How will it affect my headroom? And so on. So we look at the steel table and the basic properties of steel as a material. Okay. Then I'll explain the third first. Then we have members. Okay. From material, we'll go to elements. As in, we'll see what are the different sections which are used for carrying, say, tension. So we'll look at tension members. What are the different sections that are used for carrying compression? So we'll look at compression members. Then we'll look at beams, foundations, and uh, different types of then we look at different types of foundations. So we move on from a material level to an element level, wherein we understand the behavior and the design of every element. And the next step would be to understand how these members could be connected to each other. So we look at connections, and the basic types of connections are riveted or bolted connections and welded connections. So we are going to have an overview of each of these things. The next step would be to understand how everything behaves together, how the material members and connections come together to form a structure. uh, we don't have we don't have this in our syllabus per se, but whenever possible, wherever relevant, we'll talk about how these come together and form a structure, and how the behavior of the material, behavior of the member affects the behavior of the structure. Am I clear? So unfortunately, there's no way for me to make sure that you are understanding any of this. So I'm going to heavily rely on you answering the questions that I ask. Is that okay? When it's a normal, when it's a traditional class setting, it's very easy. I could just look at your faces and take an estimate of you've understood this or not. And to be honest, um, it has been quite an effort to make you guys like this particular subject. So right now there's just no way for me to understand if you're following me. So I'm going to heavily rely on your continuous feedback as and when we progress. Is that okay?
Yeah.
Okay, cool. So the books that I recommend for this subject are The Design of Steel Structures, which is by N. Subramanian. And if you want to go beyond and look at very fundamental concepts, there's this book by Salmon Johnson and Malhas, which is named as Steel Structures. The left one is very easy to find. You can get it in any bookstore. Perhaps you might have it in your library. So this course has been heavily based on this particular book because I think this is a very precise. It gives very precise explanations of different concepts. By the way, is there any book that is specific to this course for architecture? Do you know of any book from maybe from your seniors that is specific to this university syllabus for architecture?
No, none that we
No.
have asked or known.
Okay, great. So we'll just uh, follow these particular reference books as of now. Please give me a moment. Um, so the first question to start with is, why is steel one of the most valuable construction materials? And why should you, as architects, understand the structural design concepts in steel? So, I'm going to focus on answering these questions in this and perhaps the next lecture. And a third question that perhaps you might be able to answer is why you should join the lectures on time. Uh, so, in classroom, a normal experience has been that you have a very busy schedule, and there are a lot of activities that are scheduled on a Saturday. So it has been a consistent struggle for me to get lectures, to get slots for the lectures. But since now it's you're doing it from your comfort of your home, I believe there's a very high possibility that you can join on time. And considering the strict time schedule that we're working with, I request you all to please just log in at 10. If you log in at 10, I'll make sure that you log out of whenever whatever is the scheduled time for the class. Okay. Um, so basically, what we are going to try to do is develop a solid background. Now, what I believe is anybody can teach you the process. Anybody can teach you the process of design, process of selection, or process of anything. But what I can really contribute here is I can uh, answer a why to everything. I can uh, probably we together can work on why is this the process, or why is this particular thing done, or what is the significance of this because of which this is done. So pardon me if I spend some time on explaining the concepts more than the process, because process, once you understand the concepts more, this the process is just something that you'll catch up eventually. So um, we are basically going to work on developing a solid background on the principles rather than the process. Also, we'll try to now it's very difficult. I understand it's very difficult for you to submit those assignments in this particular setting, for you to submit assignments and for me to check assignments. So there's something different that we are going to try this time, which we'll discuss at the end of the class. Perhaps after the recording is stopped so that we don't waste time. And of course, there's another thing that I can contribute here is the understanding of real world challenges, because this is something that we deal with day in and day out, and therefore this is something we can discuss. So you always have a practical approach while you work on your design projects. So there is a particular, so just like there are various guidelines for various subjects. So the guideline or the code in structural engineering, we have different codes. So there's a code of structural steel, there's a code for reinforced concrete, for earthquake resistance of structures, for bridges, and so on. So this code or this recommended set of guidelines uh, helps a designer in the design and construction of structures. So if a particular designer follows this code, there is a high there's a high probability that the structure is adequately safe. Okay, so there are some guidelines. For example, there's a guideline that the deflection of a beam cannot be more than 20 mm. So if I'm making sure that I'm selecting a section in such a way that the deflection is not more than 20 mm, as per this guideline, I'm making sure that the structure will be serviceable, meaning that the occupants of the structure will not face discomfort while living in the structure if I provide this type of section. So basically, these are guidelines. It gives guidelines and it gives a set of uh, what I can say recommendations. If we follow them, there's a high possibility that the structure is going to be safe and the structure is going to be serviceable. Plus, this particular book has a legal validity. So if I'm designing my structure following all the guidelines in this structure, the design is legally valid. So unfortunately, if there's a mishap later on, there's always a check, there's always a cross check if the structure has been designed as per the code of practice. If it is not, then the design can be called as illegal. So it has a legal validity. So we are not going to go page by page per se, but whenever required, we are going to refer to this for giving us solutions whenever we are in problems. So I recommend that you download a copy of this. You just have to type in IS 800 2007, and it's very easy to obtain a copy of this code. Okay, uh, do you guys so whenever there's a lecture, do you guys normally continuously go on, or is there a small break in between? How does it work?
Usually there's supposed to be a break, but then most faculty just continue.
Okay, so what do you want here? It's been an hour. Do you want a 5 minutes break?
Okay.
I guess
Oh,
no.
I think we've developed the stamina to go ahead.
Sorry?
Yeah, we can continue since we
can
started late also.
Okay. Thank you very much. I hope everybody agrees to what's your name?
Mohit.
Yeah, I hope everybody agrees to Mohit and we can continue. I just hope everybody is listening to what I'm saying. This is no way to find out.
Yeah.
Okay. But it's good that I hear different voices, so I know the the same set of people is not talking. It's good. So begin. So the first step is to understand the material, and then we can understand how it behaves in an element, and then we can understand how it behaves in a structure. First step, understand the material. So steel is all about tension. So steel has a very high tensile strength. It is manifolds of the kind of tensile strength that concrete has. Okay. So how do we gauge or how do we measure this strength? How do we measure how much tension can steel take? Okay. So to put a label or to put a number on how much tension can a steel take, we have a test called as the tension test. We have a test which is called as the tension test, which is performed with the help of a machine which is called as the universal testing machine. The machine that you see on the right side is a universal testing machine. So this machine basically has two clamps And in these clamps, we fix a steel sample which is called as a coupon. Now we want to test these coupon in tension. So where do you think should the upper clamp move? Should it move downward or should it move upward? Do you follow my question? So now if I want to know how much tension or how much tensile force can this particular sample steel element take, I've clamped this between these two uh, clamps. If I want to test how much tension does it take, do you think these clamps should move towards each other or away from each other?
Away from each
Okay,
other.
okay.
Away from each other.
Yes, straightforward, right? Only then we can know how much resistance that it is offering and how much elongation it undergoes. So the upper clamp moves upward, by the virtue of which we can elongate or we can stress the sample. If we have to look closely at how the coupon looks like, so this is just a conceptual sketch of that coupon. The circles that you see are the points where the clamps are connected, and they are the points of application of the load. Then the length LG that you see is called as gauge length, is called as gauge. So this is the length over which we are going to make our observations. Okay. Then the area of cross section. The area of cross section. Okay, you understand what is area of cross section, right? The shaded area is not the area of cross section. Area of cross section is when you cut it, and the area, the width and the thickness that you see is the area of cross section. So the only two parameters that we look at initially is what is the area of cross section before the load is applied and what is the length before the load is applied. Okay. Uh, just to give you before and after pictures of the coupon, the bottom one is before the test and the top one is after the test. Now, this is just to give you a sense of how much steel elongates before it fails. Okay. So, uh, by looking at these two pictures, you could say that steel is a ductile material. Perhaps, or definitely, we cannot say the same about concrete. Concrete is very weak in tension. You will never see a concrete specimen elongating that much. Now, what is the importance of this elongation? We are going to see briefly. Uh, Before we get into what the test is, how it is done, what is the importance, what is the output of this test, let us look at a small video of the actual test and uh, some readings that the test gives that are important for us to understand the material. So on the right you see the test rig and on the left there's a graph. Okay. Now this graph is the force that is applied against the elongation that is happening. Okay. The force that is applied is given by the machine itself. The machine tells you, okay, I've applied 1000 kilonewton, or sorry, 1000 is a too large a number. Say 50 kilonewton, 100 kilonewton force, and then there are these gauges that measure the elongation. So this is just a simple graph of force against elongation. What I want you to observe is the upward moment of this particular clamp. So please observe the upward moment of these clamp. So this was just a brief preview of how the coupon behaves when it is loaded. Okay. Now, from this experiment, there are a few things that we want to know. The first thing is, what is the maximum load at which this failure occurred? So we know what is the strength of it. Okay. And the next thing that we want to know is how much it has elongated, which means we want a measure of ductility, or how ductile is this particular section, or how ductile is this particular material. So to understand that, we look closely at what is called as a stress strain curve of mild steel. On the y-axis we plot stress, and on the x-axis we plot strain. I hope you understand what is stress and strain. Junior KG physics, right?
Yes, we have done this last time.
Last time, great, great. So can somebody please tell me what is stress?
Force per cross sectional area.
Okay. What's your name?
Rahul again.
Oh, Rahul again. Hi, Rahul again. And thank you for the answer. Anybody else? Come on, no one? What is stress? Like we use this word like a zillion times. Like stress mat le, stress mat de. TOS का stress mat le, वैसे भी कुछ नहीं आता है, and so on. So, what is stress?
The capacity for the material to take the load.
Okay.
So when a deforming force is applied to a body, the body
Yes.
tries to fight back the deformation. So the force with which it fights back, sorry for the screaming in my
No,
background, but
no
yeah, the
problem.
force with
The
which
answer
it
is
fights back is, yeah, the stress of the like the body.
okay. What's your name?
Bidisha.
Vidisha, very good answer. See, there's a difference between force and stress. Okay, force is something that is applied externally. Okay, now force is something that, say, I am applying in this lecture by making you sit for 2 hours. That is force. Okay, stress is something that you are taking. Stress is internal. Now you are, so like a lot of you are sitting it, stressing yourself, trying to understand everything. Okay, so the stress that you're taking is significant. Some of you are just chilling out, sleeping on your bed, and maybe playing PUBG or something. So that stress is relatively less. Though the amount of force is same, the amount of stress that someone takes is different. Okay, so stress is an internal quantity and force is an external quantity. As Vidisha rightly said, the amount of resistance that a material offers to an externally applied force is called as stress. Mathematically, what someone answered, the first answer that I got, force is equal to stress into area, it is mathematically correct. Oh, sorry, stress is equal to force into area, force upon area is mathematically correct. But actually, stress is a resisting force upon area. Do you understand the difference? Hello.
Yeah.
Yeah.
Is there someone who does not understand the difference?
I didn't.
Sorry?
I did not like the last part.
Okay.
Stress is force upon area, but or
Yes.
say that stress is resisting force upon area.
Okay. Thank you. So, mathematically, as we know it, stress is equal to force upon area. Okay. Now, if I am saying that stress depends upon how much resistance the material offers, it should be stress is equal to resisting force upon area.
Okay.
Okay. Now, Newton's third law states that every action has an equal and opposite reaction. Therefore, the resisting force in a material is equal to the applied force, and therefore, instead of writing resisting force upon area, we just write force upon area. Okay?
Yes.
Did I answer your question?
Yeah.
Okay. So what we are going to do here is we are going to look at the stress, and then we are going to look at the strain, and we are going to look at the relation between them so we know how the material behaves. I hope all of you understand strain. Plain and simple, change in length upon original length. Okay, and that is why the term gauge length is important, because we should know what is the original length, and we should know the original cross-section area, because stress is force upon area. The machine gives us force, we know the area, that is how we can get stress, and we can plot stress versus strain. Now, I just want you to listen to this particular portion very carefully. Uh, the first part of this curve is a straight line, and that is somewhere, that is the region in which the material is perfectly elastic. Okay, when we say that the material is perfectly elastic, it means that when you apply load, the material will deform. When you remove the load, the material or the member will go back to its original length or original state. That is what is called as elastic behavior. Just like a rubber band, when you stretch it, it deforms. When you remove the force, it goes back to its original state. So if you load steel in this linear part, the material behaves in an elastic manner. Okay, but there's an upper limit to it. So there's this term called as Fy. This is a very important term. F is normally used to denote stress, and Y is what is called as yield stress. Okay, so it is the value of stress at which the material is no more perfectly elastic. It starts yielding. You understand what is yield, right? So it is the level of stress after which the material starts yielding. Now you see, there's this straight portion. There's this straight portion in which there is an increase in the strain, but there is no increase in the stress. Can someone tell me what does that mean? In this plateau region, which is called as a yield plateau, the strain is increasing, but the stress is not increasing. Anybody?
So even without increasing the load or the force, the length is increasing.
Exactly, which means that at this particular value of yield stress, the elongation is happening without any increase in the stress of the material, meaning it is not offering any resistance. It is just letting the force elongate it. Okay, so after we reach the end of yield plateau, it again starts offering some resistance. Then we get a value of maximum resistance, which is Fu, which is called as the ultimate tensile strength. This is the ultimate. So when we say something ultimate, it is the highest. It is the highest stress that the material can take, and after that, it gradually leads to failure, or it leads to fracture. Do you understand this curve?
Yes.
Yes.
Yes. Okay. Great. So this now let us look at the strain values. Now the strain at the yield stress is denoted by epsilon y. Normally epsilon is used to denote strain. Now this particular region, which is after the yield plateau, is called as a strain hardening region. The region in which it offers some resistance after the yield plateau is called as strain hardening region. Now you see the and the beginning of this, the strain at the beginning of this curve is called as the strain hardening strain. Okay, this is epsilon sh, which is the strain corresponding to the strain hardening. Let's call it that, epsilon sh. Epsilon sh is about 10 times epsilon y. If we look at the ultimate stress, the corresponding strain is approximately 100 times epsilon y, is about 100 times epsilon y. We'll look at what these numbers mean. And we are not interested in how much times it is. We just want to conceptually understand what does this signify. And if we look at the ultimate strain, it is perhaps looking at the scale of the graph about 170 to 180 times epsilon y, which means after when the stress reaches from Fy to Fu, the strain can increase by about 160, 170 times, which means there is a lot of capacity of the material to elongate without failing. And this particular property of a material to undergo a significant amount of deformation without failing is called as ductility. Okay, have you heard this term before?
Yeah.
Yeah, so strength and ductility. So the y-axis is the measure of how strong the material is. Okay, and the x-axis is a measure of how the extent of the graph in along the x-axis is a measure of how ductile the material is. Okay, so two properties that we must know about a material is what is its strength and what is its ductility. Okay, how much it can take and how much it can elongate. Now, one particular parameter that is of importance is the slope of this graph, is the slope of this initial line of curve. Does anybody know what this slope is? What this slope is called?
Modulus of elasticity.
Yes. This slope is called as Young's modulus of elasticity. Young's modulus of elasticity, and it is a measure of stiffness. Now, just right now, just try to understand, just try to remember these terms: strength, stiffness, ductility. We'll look at them later. Just try to understand, just try to remember these terms right now. The extent of y-axis is strength. Extent of x-axis is ductility, and the slope is a measure of stiffness. Okay. To kind of simplify this curve that is provided in the book, I've just shown you a hand-drawn sketch here. Okay. So I recommend that you draw this particular curve because we, in the next few slides, we have to look at each of these points, that is A, B, C, D, E, F, and so on. So I'll want you to look at the curve that you've drawn and the content on the presentation. So I recommend that you draw this particular curve.
I had a question in the
Sure.
last slide.
Yes, sure.
So, what are the two different curves? What do they mean? The true stress strain curve and the engineering stress strain curve.
Okay, what's your name?
Ishan.
Ishan. So this is a very definitely it's a good question. It's a very good technical question. What is important for us, or what is relevant for us, is the engineering stress strain curve. Okay. Now, the difference is that in the engineering stress strain curve, I'm sorry if I'll get technical into this, but please just let me know if you don't understand it. I try to simplify it as much as possible. So, in the engineering stress strain curve, when you calculate stress, you always divide force by the initial area. Simple. The engineering stress is equal to force upon initial cross-section area.
Okay.
In the true stress strain curve, true stress, which is the instantaneous stress, is equal to force upon actual area.
Yeah, got it.
There's a difference between initial area and actual area, right? Because as you elongate, the length is increasing, but the cross section is decreasing. Do you
Yeah.
understand?
Yes.
And therefore, uh, this the true stress strain curve always goes up because true stress strain curve is force upon true area or the actual area. Since the numerator goes on decreasing, the value is always going to go on increasing, and therefore you see that this curve is above the engineering stress strain curve.
Okay. Yeah, got it.
Okay. Um, I know this is a little technical, but if you have any questions further, if anybody else has any questions further, please let me know. So what is,
Uh,
yeah, please.
but then why do we have the engineering stress strain curve if yes.
Yes. Now, uh, talking about, say, if you want to, uh, okay, one way of looking at it is when we place some particular member in a structure, okay, what you are aware of is what is the initial cross section, okay. Now, as the structure is loaded from the start of its actual service life, you have no measure of what its cross section area is going to be over the period of its use. Okay, so the only parameters that you have is what was the initial cross section. So based on that, you have to decide how the structure is going to be behave when it is going to be loaded. Talking in terms of practicality of the experiment, it's very easy to measure the initial cross section, and it is very difficult to measure the instantaneous cross section because you saw in the test or the test or the material failed in a very short amount of time. So it is practically not possible to measure the area every time after after you increase the load from say 150 to 100 kilonewton. It is not practically possible to go and measure the cross section area.
Okay, yeah.
And until the end of, if you see these two curves diverge after the yield plateau. Okay, the only relevant information that we want is until this yield plateau. We do not care much about what happens later because in design, now this is a step further, but just to let you know, in design, we are more interested in what happens to this curve only in this yield region. This is a portion that this is the strength in this portion is something that we do not consider in design. Okay, we'll get into the details later. As of now, the only thing that you want to understand is the difference between true and engineering stress strain curve and what this curve means. Okay?
I have a question.
Yeah, please go on.
Yeah, I just didn't understand. So when we like design a structure, like when we
Yes.
design the columns or the beams or whatever, we design it with the sense that we take one specific value for the load. Like we keep it constant, right? Because we are designing for that load specifically.
Yes.
So supposing
Yes.
I'm designing a mall and I know that these many people would be coming there, and that would be
Yes.
like the load that would be is like capable of being taken by the column or the beam. So then in that sense the engineering stress and strain and would be same as the true stress and strain, right? It won't change it because the load is not changing.
Okay.
So then
See,
why do we need two curves? in that sense, because the load doesn't change. Like you
No, no.
calculate your thing for the load that is going to be constant like throughout.
Yeah, true. I understand your question, but then you're going to have to uh, look at it slightly beyond the point that you're thinking right now. Okay, on normal occasions, you know what is the value of the load that is going to be put, but we don't design any member or the structure for normal conditions. We design them for extreme conditions. Okay, for example, if I want to design a particular member for the live load, I will not consider the live load on normal days in a mall. I will consider the live load when there's a concert in the mall, concert in the center of the mall, and the entire mall is filled with people. All the balconies have people. The balconies are cantilevered, and there are people standing all over, and that is the maximum load that is going to act on that particular section. So the load that you are talking about might be somewhere here. The load might induce a stress that is somewhere here. But I will design for a stress when it is maximum loaded. Okay, it is the worst condition. So every structure and every member is designed for the worst condition. It is designed for an earthquake. It is designed, tall buildings are designed for the worst wind. And when we are talking about these extreme conditions, we have to make sure that the structure still stands after that particular event has passed. So though your question is correct when you say that the load is not increasing, so the load does not increasing in normal loading conditions, but in extreme load conditions, the load definitely increases.
Yeah, I got it. Okay.
Okay.
Yeah.
Yeah. I request you to please draw this particular stress strain graph, because we are going to refer to this particular sketch time and again in the next slides. In the meantime, if there are any further questions, please shoot.
Bhargav, can you go back to the previous slide just for 1 second?
Yeah, sorry. Yeah.
Yeah, you can go ahead.
Can I go ahead, everyone? Should I wait for someone?
Yeah, just a minute.
Yeah.
Yeah, you can go.
Okay. Everybody okay?
Yes.
Okay, cool. Now let us look at each of these points. By the way, whenever you think that you are yielding, just let me know. We'll take a short break. Okay. Um, do you need it now, or it's okay? We can go ahead.
That was a nice pun.
Sorry.
That was a nice pun.
Yeah. Thank you. Anyways, can you please also answer my question?
We can go ahead.
Yeah,
Go
we
ahead.
can go
Great.
ahead. Yeah.
A very optimistic batch. Thank you. So yes. So let us talk about
We can't hear you.
Bhargav, I think you're on mute.
I think he got disconnected or something. No.
Can you hear me now?
Yeah.
Okay. So at what point did you lose me?
No, you didn't even start.
I didn't even start. Okay.
Like after the optimistic batch part.
Okay. So the point A is what is called as proportionality limit.
We can't
Un-
see your screen.
Okay now?
Yeah.
Okay. So the point A is called as proportionality limit. From the origin until point A, the stress is directly proportional to strain. Uh, does someone want to? Okay. Gargi, do you have any question?
Sorry, it was by mistake. Sorry.
Okay, no problem. So, from the origin until point A, the stress is directly proportional to strain. Do you know what this law is called?
Young's modulus.
Yeah, Young's modulus is the slope of that particular line.
Hooke's law.
Yes. So the law is called as Hooke's law, which states that until proportionality limit, stress is directly proportional to strain, which means that can someone please mute their mic? There's a lot of disturbance. Uh, can you please mute your mic? Okay. So until point, if you load the member until point A and you unload it, it will go back to its original state. So A is called as the proportionality limit. Now B is called as elastic limit. B is called as elastic limit, which means if you load the structure until the point B and you release the load, it will get back to its original position, but the curve is not straight, it's slightly curved. So Hooke's law is strictly valid only until point A. Then there's this point C, which is called as the upper yield point. And after that, there's this point D called as lower yield point. Now, the point C occurs for a very small amount of time and suddenly it jumps to D. Therefore, we rely more on this lower yield point than the upper yield point. The stress corresponding to this low yield point is called as yield stress. Okay. Can you guys hear me?
Can you just explain again the difference between A and B?
Between A and B. Okay. Can you guys also hear some disturbance?
No.
Okay.
No.
For some reason, I hear a lot of disturbance. Anyways, so until point A, stress is strictly directly proportional to strain. Okay. And the material is elastic. Until point B, stress is not strictly proportional to strain, but the material is still elastic. Do you get the difference?
Yeah.
So if you load the material until B, it will come back to its original state. That property is called as elastic, and therefore until point B, it is called as the elastic region. But theoretically, stress is directly proportional to strain only until point A. So Hooke's law is valid only until point A. Okay, so that is a minor technical difference between points A and B. The other points that we meet after B are C and D. C is called as the upper yield point and D is called as a lower yield point. Okay, the lower yield point is much more stable and it occurs for a longer range of load, and therefore we we define our Fy, which is yield stress, at point D and not at C. Okay, C occurs for a very small of a fraction of a time, and therefore it is not very significant. The next point is point E, which is start of the strain hardening region. It is when, after giving up, the material again starts to offer some resistance. E is called as a strain hardening. It is a start of the strain hardening region. The next is point F, which is the ultimate point, or it is the maximum stress that the material can take. And point G is called as a breaking point, or it is a point at which the material has ruptured. Okay. Now, if you notice one thing, Fy corresponds to epsilon y, but Fu does not correspond to epsilon u. Do you understand what I'm saying? The strain at Fy is called as epsilon y, but the strain at Fu is not epsilon u, because the definitions are different. We define Fu as the maximum stress. So in this graph, the maximum stress is this, but what is the maximum strain? It is this. So the ultimate stress and ultimate strain are not the same point. They are different. Just for your information. So this is something that I explained before. OA is called as the linear elastic zone, in which Hooke's law is strictly valid. Stress is proportional to strain, and it is a measure of stiffness. The slope of this particular line is called as Young's modulus of elasticity. So the slope of an xy graph is normally the y component upon x component. The y component here is the stress and the x component is strain. So Young's modulus is stress upon strain. Now the value of this for steel varies from 2 into 10 to the power 5 to 2.1 into 10 to the power 5 megapascals. Normally it is approximated as 2 into 10 to the power 5 megapascals. There is a very important thing that I forgot to add when we started this, is this particular curve is only valid for what is called as mild steel. Now, steel has different grades depending upon what is the carbon content of that particular material. If the carbon content is low, it will have a lower strength but a higher ductility. And such a steel that has relatively lower carbon content is called as mild steel. Okay? Did you get this point?
Can you please repeat that?
Yes. So the grade of steel depends upon what is the relative compositions of different elements. A steel is called as mild when it has a relatively low carbon content. Carbon is a brittle element. When you go on increasing the content of carbon, your strength will increase, but your ductility will reduce. Okay, we'll look at it further. We'll look at it in the next few slides. But the point being, the bottom line is, this curve is for what is called as a mild steel. Mild steel, it is called as mild because it has a moderate tensile strength. So it is called as a mild steel. We'll look at high strength steels a little later. Okay, so this curve is valid only for a mild steel. Yeah, we have seen this. So the portion AB, that is from point A to point B, though the material is elastic, but it is non-linear. The line is not straight, it is a curve. Therefore, it is called as non-linear elastic zone. Hooke's law is not strictly valid, but the material is still elastic. Okay. Then the region DE is called as the yield plateau or the plastic zone. Meaning that now if you load a material up to this extent, if you load it up to point D or up to this region and you release the load, it will not get back to its original position. There will always be some plastic deformation in it, and therefore it is also called as plastic zone. Okay. So the material flows plastically without offering any resistance, and permanent deformation, which is called as a plastic deformation, occurs at a consistent yield stress, and the plastic zone accounts for ductility of the steel. So higher the extent of the plastic zone, higher is the ductility of that material. So now we look at our most important parameters, that is yield stress and yield strength. Okay. If you look at the graph and look at the value of Fy, we are looking at the definition of this Fy. So yield stress refers to the maximum stress that can be developed in the material without causing plastic deformation. Until this value of stress, the material does not undergo any plastic deformation. If you release the load at this stress, the material will go back to its original state. So this stress is called as yield stress. Okay. Now, the corresponding strain is called as yield strain, that is epsilon y. Since Young's modulus is Fy by epsilon y, if you want to get the value of epsilon y is equal to Fy upon E. Okay. For mild steel, the value of Fy is 250 megapascals. You can jot it down if you want. For mild steel, the value of Fy is 250 megapascals. I hope you understand what is megapascals. So 1 megapascal is equal to 1 Newton per mm square. 1 megapascal, I think I mentioned it somewhere. 1 megapascal is equal to 1 Newton per mm square. So this value is fixed, 250. This value is fixed, 2 into 10 to the power 5. We get this value, which is 0.00125 mm per mm. You don't have to remember this. This is just for your information here. Then the zone EF, which is called as a strain hardening zone, in which, so this is just a summary of what we've already, what I've already explained while looking at this graph. So this is just for your reference later on when you go through these slides. So the stress increases above Fy when the strain hardening epsilon SH is exceeded until the ultimate tensile strength Fu is reached. These are just values for your reference. And the final point is G, the final region is Fg, which is also called as a strain softening zone, in which there is a significant reduction in the cross section, and finally the section breaks at a strain which is approximately 200 times of the yield strain. The 200 number only implies that it has a lot of ductility, it can undergo a lot of increase in length as compared to its original length. Okay. So now this was the curve for mild steel. If we look at the curve for what is called as ordinary or high strength steel, you do not get such a well-defined plastic zone and a well-defined strain hardening zone. So the curve that you see towards the bottom is that of mild steel, and the other curve that you see is that of a high strength steel. You see, it is just a straight line and then a curve, then a parabolic, or perhaps a line that does not have such a kind of plastic region and strain hardening region. So in this case, it is a little difficult to define what is the yield stress. Here it's very easy. There's a straight line, so wherever the straight lines intersects the y-axis, it is the yield stress. Here we do not get a straight line, and therefore the yield stress is obtained by a slightly different method, which we need not get into. This is just for our understanding of the difference between mild steel and high strength steel. One important observation to be made here is these two curves exactly overlap along the straight line region, meaning that the value of Young's modulus is the same irrespective of the type of steel it is. Do you understand? Any questions here?
But yeah, why does that happen though? Shouldn't it change?
Yeah, actually that's a very important intrinsic property that steel exhibits. The value of Young's modulus, or the stiffness of steel of steel as a material, is same irrespective of what grade it is. What changes is the maximum stress it can take. Okay, for example, here the maximum stress it can take is somewhere between 200 300. For high strength it is somewhere between 500 600. Okay, but the slope or the stiffness or the Young's modulus is same for both of these types of steel. So irrespective of what is the grade of steel, you can assume the value of E to be 2 into 10 to the power 5 megapascals or 2 lakh megapascals. These values might be different, but their ratios will always remain the same. And that is a very useful and important property that steel exhibits. Is that okay?
Yeah, yeah.
Okay. Uh, so, 11. Shall we continue? We want a small break. – 40 more minutes to go. Okay, are you there or already signed off?
No, we are there.
Yeah. Okay, so should we
Yeah.
yeah. So 40 minutes to go, do you want me to continue or you need
I think
to
a 5 minute break.
Yeah, we could do 5.
Okay, so let's be back by 11:55.
Yeah.
Okay. Is there an option of pausing this recording?
We don't know actually. Organizers have that option.
Okay. So I'll resume at 11:55. Okay.
Yeah.
Yeah. Hello.
Yeah.
Can we resume?
Yep.
Okay. So until now, we have looked at the properties of steel as a material. Okay. Having looked at it, we are just going to compare it with its competitor or with the material that is again one of the most widely used materials in construction. And we are just going to try to compare how does steel stand as compared to reinforced concrete? What makes it more favorable and what are the set of challenges that steel comes with? Okay, so the first set of favorable conditions is intrinsic properties of steel or the inherent properties of steel. First one is very high strength per unit weight ratio. Okay, high strength per unit weight ratio, meaning that for a given weight of a material, how much strength can it take? If we look at different grades of steel, uh, they are normally designated as Fe410, where 410 indicates the ultimate tensile strength or the point F, and yield strength indicates the point D, that is the yield stress. So this is mild steel that has yield stress in the range of 230 to 250 and has Fu around 410. Now there are various other grades. So this is just for your information. This is nothing that you have to remember. But certainly remember this value, 250 megapascals. If I compare it against concrete, so can someone tell me how is the strength of concrete designated? Heard of M20, M30, M40 concrete?
Yeah.
Can someone tell me what M stands for?
The mix.
Yes, so it is mix 40, mix 50s and so on. In the next course, we will see what this 40, 50, 60 values are. Right now, just assume that 40, say M40, the 40 number in concrete is equivalent to 250 in steel or Fy value in steel. Okay. Did you understand this M40, say M40. So this 40 number is equivalent to Fy in steel. So steel has a density of about 78.5. Concrete has a density of 25. If I compute the strength to weight ratio, so this is the strength and this is our density. The strength to weight ratio in steel is 3185, whereas in concrete it is 1600. So for a given weight of the material, steel can take much higher load as compared to concrete. Okay. So this might need a little understanding, but can someone answer how is it practically important that the strength to weight ratio of a material is high? How does it help us? Anybody?
Lighter materials carrying the load of heavier, like higher loads.
Exactly. So if a lighter material can carry the same load, which means that the sizes of the sections would be small, which means that the size of the foundation would be small, which means we would have larger effective area that can be used. If instead of a 500 by 500 concrete column, you can use as an ISMB 400 steel section, we look at what is ISMB 400, but it is smaller than a 500 by 500 concrete section. You will always go for an ISMB 400 section if other conditions permit, because that gives you a larger carpet area. Smaller the size of sections, smaller would be the size of foundation and lesser would be the cost of foundation. Okay, one thing just for your information, irrespective of the steel, irrespective of the structure being steel or concrete, the foundation is almost always concrete. Okay? Irrespective of the structure to be steel or concrete, the foundation is almost always concrete. So lighter the members, lighter the foundation, lower the foundation costs. And that is why high strength to weight ratio is important. Another important property is high ductility. Okay, as I've said time and again, the extent of the stress strain curve along the x-axis is a measure of ductility. So if I look at the series of graphs on the left, the green material is ductile as compared to the pink one, which is more ductile as compared to the blue one, which is more ductile as compared to the sky blue one. So higher the extent on the x-axis, larger is the ductility. Okay. So this is just a physics definition of what ductility is. So this is mild steel and this is high strength steel. When I look at these two graphs, there are two observations that we can make. First, is a high strength steel has a higher strength as compared to mild steel, but a mild steel has higher ductility as compared to high strength steel. Do you get the difference? Should I repeat it? Should I explain it in a different way?
Got it.
Okay. Nonetheless, I'll just explain it once again. High strength steel has a higher strength as compared to mild steel, but mild steel has a higher ductility as compared to high strength steel. This happens because the difference between a mild steel and a high strength steel is that a high strength steel has a higher component of carbon content. Okay, carbon is a brittle material, but it is a stronger material. So when you add carbon to mild steel, its strength increases, but its ductility reduces because you are adding a material that is strong, but that is not ductile. Clear?
Yeah.
Okay.
Yeah.
Yes.
So ductility is the next intrinsic properties. Can someone tell me why am I emphasizing so much on ductility? Any particular situation that you can think of where ductility is quintessential?
It'll show the deflection.
Yes, that is correct. But can you think of a sort of loading condition wherein ductility is of prime importance?
Maybe suspension bridges.
Suspension bridges, in that way, it is important in all structures. But can you think of a loading condition where this is ductility is very important? This is something you already know, but you just
Where,
cannot connect my question to an answer, to the answer that you already know.
When it's
where
in
there might be shear forces.
Um, so let's forget about
Where there is axial loading,
where there is
axial axial loading
axial
in
loading.
the yeah.
Okay, so any more answers to come in? See, this is a question to which you already know an answer, but you cannot connect my question to that answer. In which loading scenario is ductility is of prime importance?
every tensile loading condition, right?
Yes, but this, okay. So the answer to this is in earthquake loading. Okay, when a particular structure is designed for earthquakes, or when we do seismic design of a building, it is quintessential that the structure can undergo significant amount of deformation without failing. Do you understand?
Yeah.
Yeah. Yeah.
If the structure is brittle, if the structure is brittle, then earthquake is all about motions. Earthquake is all about ground motion. So when the ground is moving, I told you, stress is the amount of internal resistance. Okay, so if a material is very strong, very stiff, but if it is brittle, it is likely that the structure will collapse if it is a brittle structure. If it is a ductile structure, it will deform, but it will not break. And therefore, ductility is a very important property when it comes to seismic design. Therefore, we should not only focus on the y coordinate, which is strength, we should also focus on the x coordinate, which is ductility, which is a measure of ductility. Now, if I want to compare these curves with the same curves for concrete to just give you a feel of how different is steel from concrete, the curve is something like this. Okay, that's the curve of concrete. So you can see how strong and how ductile is steel as compared to concrete. Okay, moving on. The third intrinsic property is it's elastic, and this form of behavior is predictable. If I look at the curve of concrete, there's hardly any straight line here. It's all parabolic, and therefore it's difficult.
Excuse me, the slides aren't moving jolly as to what you're saying. Okay, now we see the concrete, but we couldn't see it before, so.
Okay, thank you.
There's a lag.
There's a lag.
Sorry? There's a lag. Okay, there's a lag. Just let me know if it occurs again. So, steel behaves elastically, unlike concrete, and this kind of leads to a very predictive behavior. Next semester, we'll in detail look at the stress strain curve of concrete, and you'll notice that concrete does not have this linear segment that steel has. This linear segment means that we can predict the behavior of steel in much probable manner than that of concrete. Okay. Now, a simple question. There's a rubber band, there's a diamond, there's concrete, and there's steel. I've mentioned the values of modulus of elasticity below each of these figures. Could you tell me which is the most elastic material?
The rubber band ball.
Okay, quick answer, good one. Anybody else? Okay.
Yeah, obviously the rubber band ball.
Anyone with a slightly different imagination? Abhilasha, are you there?
I mean, I guess steel is also elastic, but it does not retain its shape after a certain point.
So which is more elastic?
Okay, repeat the question again, please.
Okay. So we have 4 materials: rubber, diamond. Okay, I've already revealed the answer. So we have rubber, diamond, concrete, and steel, and I've mentioned the values of models of elasticity. Could you tell me which is the most elastic material? So the majority, the consensus seems to go with rubber here. Anyone with a slightly different approach?
Steel is the most elastic material
Okay, and why do you think so?
because rubber is more stretchable when it comes to elasticity. The longer it takes to change its length, I think that's more elastic.
So your answer is partially correct when you say that the longer it takes, but
The
instead of
strain
longer,
smaller.
it should be how difficult it is to
Yeah,
stretch something.
yeah.
So, unfortunately, the common sense understanding of elasticity is different from the physics definition of elasticity.
Hmm.
Okay, so diamond is the most elastic material and rubber band is the least because it has the highest value of Young's modulus of elasticity. So higher the value of E, higher is the elasticity. Okay, meaning it is more difficult to deform diamond as compared to that of a rubber band. Higher the value of E, higher is the slope of that curve, higher is the value of elasticity. So this is the physics definition of elasticity, which is very different from the common sense elasticity term that we use. And therefore, diamond is the most elastic, then there's steel, then there's concrete, and then there's the rubber band. Any questions?
So like the harder the material, the harder it is to stretch the material, higher the modulus of elasticity.
Yes, higher is the modulus of elasticity. See, you can just look at the curve and get, where's that curve? Yeah, you can just look at this curve. It is stress upon strain. Okay, so higher the load that you have to apply to deform it, higher is going to be the value of E, and higher is going to be the measure of elasticity. Okay.
Yeah.
Okay, and further, steel is sustainable and energy efficient. Now, when I say steel is energy efficient, I'm talking about the energy that goes into manufacturing of steel. Producing steel is a very energy intensive process. You might have seen videos of these, or maybe perhaps in ads, a steel manufacturer's ads wherein he kind of gives a glimpses of his manufacturing unit. It's a very energy intensive process. A lot of energy goes now. If you happen to be studying green buildings and topics in that domain, you know of energy that goes into the building when it is being constructed. That is the energy that goes into the building in terms of its materials. So steel is a very energy intensive material as compared to other materials. Okay, but the add-on that we get here is steel is also recyclable. It can be recycled infinite, it can be theoretically recycled infinite number of times. And nearly 50% of the steel that is produced every year is recycled steel. It is steel that is, the scrap has a lot of value. The steel scrap has a lot of value, but concrete, not much. Or perhaps it's as of now, we might have a technology in future which is practical and which can scale the reuse of concrete. But as of now, scrap has a lot of value because nearly 50% of the steel that is produced comes from scrap. Okay, and the recycled steel uses only about 1/3 of the energy necessary from virgin materials, and therefore steel is sustainable and energy efficient. Plus, if the life of a member is over, or the expected function of the structure is over, the steel members can just be disassembled and then you can use it at some other structure. That way, you're not using new material and you are not producing a structure that has a lot of inherent energy. That way, it is sustainable and energy efficient. Uh, Other things that give it an edge over RCC is prefabrication. Now, they could build the World Trade Center in such a small amount of time because majority of the structure was prefabricated. They had prefabricated columns, beams, and the erection process was very quick. Entire thing is assembled in the factory under controlled conditions, and then it is just transported to the structure and it is just erected and connected. So it's a very quick process in steel. There is almost no site fabrication in steel except for the connections. Yep, this is what I explained. Especially in cities like Mumbai, faster construction is key to save and earn money. Meaning that the shorter it takes to complete the project, the more is the revenue that you will get from that building. Because say if you finish a project in 3 years against you finish a project in 5 years, you get 2 years of more rent from that particular property. So that way, in a lot of financially important places, speed is the key to save money. And whenever there's speed, now we have worked on projects wherein just because they wanted the construction with very ambitious deadlines, we have switched from concrete to steel. So wherever time is the key, you opt for steel construction. So to get an idea of how fast a steel construction can be, there's this company which claims to be the fastest builder, and it constructed a 57-story building in 19 working days. Okay, and then this company is in a process of constructing, is in the concept phase of constructing 220 stories tower in about 3 months. You know, you can imagine how fast that is. Most of you might have seen this video, especially after the outbreak of COVID-19, because this was circulated. This was circulated with a fake news that this is the hospital that China erected in 19 days. That's a different story. This is a different residential and commercial space that a company from. Can you hear the sound?
Not yet.
Now?
No.
Okay. Now?
Yeah, we can hear it now.
Yeah, we can.
Hello.
Yeah.
Um, so that is the speed that you can achieve with this Momo construction. So speed wise, it's all okay. It's fancy. It's really commendable. But do you see any shortcomings in this particular case? As an architect, can you see of some shortcomings of these types of modular methods of construction?
It's like the same floor plate. You can't have much variation any of the floors. So
Exactly. So
yeah.
it is just um, a repetition of this. There's no diversity that you can achieve in this.
Yeah.
It's very restricted, and you probably wouldn't have a lot of scope to, you know, play with things. It's very modular. I mean, the method itself says that it is a modular method of construction. But yeah, please.
I guess so. This was for steel, but I think even RCC has that thing. So there's this one building which was built in Mumbai, which actually used pre-casted RCC blocks. So if you have, supposing a toilet block, or maybe if you have like I don't know, bathroom or something, yeah, whatever. They precast it and then they bring everything to the site and they just assemble their Lego blocks. So the whole building is made in that sense. I think that's even possible with RCC.
Yes, yes. What's your name?
Daleka.
Dalika, hi. So she's put a very good point that yes, prefabrication is also possible with reinforced concrete, and it is initially it was done for a very few projects, but now it is being adopted on the large scale, especially in buildings that are for mass housing, for example, slum rehabilitation centers, hostels, wherein there is a lot of repetition. You don't really want to play around with a lot of aesthetics, but the function is more important than aesthetics. In such places, prefabrication is also done in concrete. It's a very good example.
Yeah, but I guess you cannot, like, if you want to change the floor plan, you can't do that again, because if you want to break down something, you cannot do that because the whole thing will just break apart.
Yes, yes, true. So again, we have space planning restrictions in concrete. You really cannot play around with the space that you have. It's all modular. The only difference here is that for steel, it is almost always prefabricated. You cannot really fabricate steel at site except if it's a very big project and there's a prefabrication plant located at the site. But almost always steel is prefabricated. And concrete, we have an option of in situ construction or prefabrication. Prefabrication is catching up. It is still in very uh, premature stages, wherein we don't see a lot of buildings that are prefabricated. But in steel, it's almost always prefabricated, and therefore we have included this point in this comparison. Now, one important add-on that steel has, it can span longer than RCC. With a normal slab beam type of system or a flat slab type system, RCC can normally span 8 to 12 meters. I'm not talking about pre-stressing. I'm not talking about pre-stressed slabs. I'm talking about normal RCC slabs. They can span, the maximum span we can achieve is somewhere from 8 to 12 meters. But extremely long spans, say from 13 to 20 meters, and large column free spaces can be accomplished using steel framing. So you can either have very deep girders, or you can have a series of trusses like you have in the picture that is shown below, shown in the background. So whenever the spans are very long, normally, for example, in airports, you will see that there is the amount of column free space required is very large, and almost all the airports have trusses at the top so that you can achieve these column free spaces. And yes, it is a preferred choice of material for commercial office and industrial buildings. Almost all the industrial buildings you see are made up of steel because they require a lot of column free space. Another important add-on or an X factor that steel has, it is that steel is available in standard sections that you can play around with. In addition to these standard sections, you can also order specific sections that you might require, specific shapes that you might require. And those can be, especially with the kind of software abilities we have, and with machines for 3D printing, we can virtually achieve any shape that you want in steel. In concrete, there is not that much flexibility in terms of what is shape of the section that you can use. And the last one is opportunities for architectural expression. That is something that we started with, is that there is no limit to the type of structure that you can construct with steel. Perhaps it's a little late to start this video. We'll start our next lecture with this video. But I guess we should stop now. And if there are any questions, this is the time.
So we had a lecture with Jimmy who told us that steel is really expensive to work with. Like it's insanely expensive compared to RCC or
Yes.
bricks or anything.
Yes. Yes, he's right when he says that. And that is the reason why it is still used in a very small scale in our country. Because the most now, when you actually get to work, you realize that the most important factor that drives the project is economy. we are a very economy intensive country, that we focus a lot on how we can make that structural economical. And that is where steel loses the race to concrete. Even with the kind of add-ons that steel comes with, um, when it comes to numbers, it's almost always concrete that wins. I'll give you a recent example of a project that we worked with. We are still working on it. So there's this commercial complex that we are working on in Worli. So if it is built as it is planned, it will be the most beautiful building in Mumbai. I know it's a little, it might seem like an overstatement, but if it is built as it is planned at this moment, it will be the most beautiful building in Mumbai. So you have these columns that come. It's a mix of a mall and a commercial tower. So there are these columns that come from the top of the tower, and they are suddenly transferred to a truss, which is about 5 to 6 story truss. Um, then it was almost certain that it is to be built in steel, because they really wanted the sections to be smaller. They wanted to give it a very different look, very open look. And then we started studying on what are the various options that we can work with. So we worked with steel, and then we gave them an option of how much steel would cost, and that amount was somewhere in the range of 50 to 60 crores. So 50 to 60 crores for just a truss. Okay, building construction is a different ball game. The cost of the building was a different story. Then it was too much for the client, and then they asked us to review what are the other options that we could use. And then we worked with a composite option, wherein we would have composite beams and composite columns. And then we had only concrete option. So in the only concrete option, the sections were much bigger. And perhaps the architect wouldn't be very happy with these sizes of sections, because then that might alter the kind of concept that he might be aiming at achieving. But the cost with concrete was of the order of 5 to 10 crores. So you see the difference. The difference in steel, it was about 40 to 50 crores, and in concrete it was 5 to 10 crores. So naturally, they compromised with the aesthetics, and they went ahead with a concrete construction. So this is just an example of how steel loses to concrete when it comes to cost. Did I answer your question or your observation?
Yeah.
Yeah, what's your name?
Mohit.
Mohit, okay. Sorry if I ask your name multiple times, because it takes a little more effort to remember people by voices than by faces. So just pardon me if I ask your names multiple times.
That's fine.
Any more questions?
Yeah, I have a question. This is just out of curiosity, actually. I was wondering, is there a lifespan to a concrete building or a steel building, after which it starts giving some kind of problems, or you need extreme maintenance or something?
Sorry, but there's a lot of disturbance in your background. I couldn't hear you properly.
I guess I'll type it down.
Is it Madhura?
Yeah.
Yeah, okay. Go on.
Am I audible now?
Yeah.
So, just out of curiosity, I was wondering, is there like a lifespan to a concrete building or a steel building, or after which it will need a lot of maintenance, or it starts getting some kind of problems?
Yes, definitely. Yes, Parth is right when he says that steel buildings require more maintenance over time. Normal concrete buildings are designed for a life of 50 to 75 years. Okay. So that is their design life. And even we design steel buildings for the same lifespan, but the difference is as Path rightly says, the steel buildings require more maintenance over time, especially in cities which are close to the coastal line where the moisture content is very high. So maintenance wise, lifespan wise, both of them almost have the same lifespan, but maintenance wise, steel definitely requires much more maintenance than concrete. But the general design life is 50 to 75 years. Yeah, also it depends upon the type of structure also. For example, if you're designing a nuclear structure, a nuclear power plant, we would design it for a life of say 150 to 300 years. If you are designing a normal building, we would design it for 50 years. If you want a temporary structure, we might design it for 5-10 years. But normal buildings, 50 to 75 years. Did I answer your question? Okay, thank you. Any more questions? Okay, so I'll just record the attendance. So I believe we'll meet next Saturday.
Bhargav,
Yeah, is
can
it
we?
Komal?
Yeah, can
Okay.
we take the lectures at 9 from next Saturday?
Yes,
So
we
we had a
can.
discussion on the class group, and
Yeah.
half the people are saying 10, half the people are saying 9.
Okay.
It's not half-half.
Half. It's half.
9 leads though.
9
Send you the
leads.
list.
It's half.
Can you decide whether it's 10, 9 or 10?
Yeah.
Yes. We can go with 9. No problem.
Works fine.
Yeah.
Thank you, Lord.
No problem. I'm sorry to
Thanks.
disappoint half of the other people. I'm sorry, but we'll start at 9 so we can get done by 11:30. Anyways, only the 4 lectures are going to be 2.5 hours long. After that, it's just 100 minutes, so not a big deal. In the next class, we'll have a small quiz, not the sort of quiz that we since I'm just saying bye to you guys, I'll just switch on my camera. Just a moment. So next time we'll have a small quiz, not the type of quiz that we had today, but an actual quiz with an actual set of questions. Normally, when we did it in the lecture hall, it was sort of a test. But now, since all of you have a lot of freedom, it's a sort of open book test. So the questions wouldn't be very technical; they would be very conceptual. Nothing out of what we discussed today. Very simple concepts from that, and it'll be for 10 minutes. Normally the way I do it is I do it on Google Forms. So there's just the link I share with you. There's a series of questions. You just select A, B, C, D, whatever, and then you immediately get what your score is. Does that work fine?
Yeah.
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 Okay. Can you see me now? Hi. So yeah, next lecture, for first 10 minutes, we'll have a small quiz. You will immediately get your scores, and I will use that for internal marking. Okay. So, any questions? Okay. So we'll wind up for today. Thank you for your patience, and I hope everyone listened to what I was saying. And meet you next week. Take care. Bye.
Thank you.
Thank you.
Thank you. Thank you.
Thank you.
Thank you.
Bye-bye.
Yeah.
Thank
Take care.
you.
Thank you.
Take care. See you next week.
Thank you.